All right, so this lesson here on Lewis structures, Vesper theory, and bond enthalpies is actually going to be broken up into two different videos. So the first one, which is what we're doing in this video, is going to be just on Lewis structures. All right, so we will draw Lewis structures as molecules, and as review, molecules are another name for covalent compounds. So recall that in covalent compounds, electrons are shared between the atoms, and Lewis structures will illustrate how they are sharing those electrons. So in the past, you wrote molecular formulas. So for instance, like CO for carbon monoxide, or CO2 for carbon dioxide, or N2O5 for dinitrogen pentoxide. While those are good because they show you the relative number of atoms in the molecule, or the relative number of each type of atom in the molecule, it doesn't quite show you how those atoms are sharing their electrons or how they're positioned relative to one another, which is what Lewis structures are going to do. All right, when you are drawing Lewis structures for a molecule, some of these you might find to be fairly simple to draw. However, at least starting out, I would definitely follow this general strategy. So first, step one is to draw your skeletal structure. What the skeletal structure is just the atoms themselves positioned relative to one another, without any bonds or electrons added in. When you are drawing your skeletal structure, the trickiest part could be trying to determine who is the central atom. And in general, the least electronegative element is going to be the central atom. Carbon, if it's in the compound, is often a central atom. And then things like hydrogen you would not want to be a central atom because, as we'll discuss in a little bit, hydrogen is only going to want a duet. So it likes to be an outside atom. And often the halogens, while they can be a central atom, generally they are outer ones as well. So after drawing your skeletal structure, and the AP exam 2 may already give you the skeletal structure and you would just jump to step 2. So step 2 is to count the total number of valence electrons. So you're counting all the valence electrons for all of the atoms in the compound. And if you are looking at an ion, remember you will need to account for those electrons either lost or gained from those ions. All right, step 3 is to determine the number of bonding pairs. To determine the number of bonding pairs, we're determining how many pairs of electrons we can make from our total number of valence electrons. So what you do is take the valence electrons you counted up in step 2 and you divide it by 2. Step 4 is to place those bonding pairs. And at first, when we're placing them, we're only going to add single bonds between the central atoms and the outer ones. Step 5 is then to determine the number of electron pairs remaining. So to do this, you take the number of pairs that you used up or placed in step 4, and you're going to subtract that from the total number of bonding pairs that you calculated in step 3. Then step 6 is to place lone pairs around the outside atoms to satisfy their octet. Or in the case of hydrogen, hydrogen just wants a duet, so it only wants 2 electrons around it. Then once you've placed lone pairs on the outside atoms to ensure that they have satisfied the octet, you're going to place any remaining pairs on the central atom and determine whether the central atom satisfies the octet rule. This may require us in some cases to move lone pairs on the outside atoms to make multiple bonds between the central atom and the outside atoms. And we'll look at some examples with that. So once you think you have drawn your Lewis structure, you're going to check for 2 parts. One is that you have placed all of the valence electrons that you counted up in step 2. And then the second requirement or second check is to make sure that all of your atoms have satisfied the octet, or in hydrogen's case, the duet. Now, of course, and I'll mention this at the end of the video, there are exceptions to this octet rule. But in general, we're looking to satisfy octets for the atoms, except for hydrogen just wants to do it. So as a note, before we begin doing examples, a single bond is going to represent 2 electrons, and single bonds you can draw with 2 dots, so like electrons in these cases are going to be dots, or you can do a line. So a line represents 2 electrons or bond. Okay. A double bond you can represent with 4 electrons, or you can do 2 lines stacked on one another so it kind of looks like an equal sign. And then a triple bond is 6 electrons, and again you can draw the 6 dots, or you can do 3 lines stacked on top of each other to represent a triple bond. All right, and then as an additional note, if we are looking at an ion and drawing its Lewis structure, we will place brackets around the entire structure, and then the charge of that ion is going to go on the outside of the brackets as like an exponent. So it'll be in the upper right corner of the brackets. So here's an example. Say we're looking at ammonium, NH4+. Once you have your Lewis structure drawn, and this structure here is a little bit different than the Lewis structures because it takes into account the molecular shape, but we'll talk about that in a later video with Vespers theory. But regardless, you would put brackets around the total structure and then the charge in the upper right corner of the brackets, on the outside brackets. All right, so let's start with an example. We are wanting to draw the Lewis structure for F2, so diatomic fluorine. So first, step 1 is to draw that skeletal structure. So we have, in this case, there's only 2 atoms, so you can't have a central one really if there's only 2. In this case, either one could serve as the central atom, and we're just going to stack them side by side. Now, if you wanted to, you could stack them like this fluorine, and then you could put this second fluorine above that fluorine. It doesn't matter, but I'm just going to stack them right side by side. All right, step 2 is to determine the total number, or count the total number of valence electrons. So one fluorine atom we know has 7 valence electrons, and in this case there's 2 fluorines, so 7 and 7 gives us 14 valence electrons. All right. Step 3 is to determine the total number of bonding pairs. So you're taking those valence electrons and determining how many pairs you can make out of it, so dividing it by 2. And so that gives us 7 bonding pairs. And then step 3 is to place single bonds between the central atom and the outside ones. Again, in this case, there's only 2 atoms, so we're just going to draw a single bond between them. And then the next step is to determine how many pairs you have left. So we had 7, we placed 1, and then we're going to subtract off that 1. So we have 6 pairs left. Okay, so step 1, draw the structure. Step 2, count valence electrons. Step 3, determine the bonding pairs. 4 is to place the bonding pairs and make single bonds between the central and outer atoms. Step 5 is to determine the pairs left. So we have 6 pairs left. And then the next step is to place those pairs on the outside atoms to satisfy the octet rule. So currently, if we say focus on this left fluorine here, if we were looking at how many valence electrons it has around it in this Lewis structure that we have drawn so far, there's 2. That's because this single bond here, which is between both of those fluorine atoms, means that this fluorine is sharing these 2 with this fluorine. So both of these fluorines right now are sharing these 2 electrons. But remember, fluorine is going to want to satisfy the octet rule. So it means we need to give it 6 more electrons. So what I'm going to do is place, of our 6 pairs, I'm going to place 3 of them around this left fluorine. So now this left fluorine has 2, 4, 6, 8 electrons around it. And I'm going to place 3 pairs around the right fluorine. So now we've placed those 1, 2, 3, 4, 5, 6 pairs. And then to to make sure that we have satisfied our two things. So one is to check that you have added in all of the valence electrons you're supposed to. So we have 2, 4, 6, 8, 10, 12, 14. We have added in 14 valence electrons, so we're good there. Then the second check is to make sure that all of our atoms have satisfied the octet or duet for hydrogen's case. So this left fluorine has 2, 4, 6, 8. The right fluorine has 2, 4, 6, 8, because remember, they're sharing that bond between them. All right, so that's diatomic fluorine. All right, let's look at another example. So in this case, we have 4 atoms. So we will have to determine who is the central one here. Now, remember, to determine the central one, generally, it's the least electronegative element in the compound. And additionally, remember I said earlier that hydrogen does not want to be a central one. Hydrogen is going to be an outer one. So our phosphorus is going to serve as the central atom, and around it to 3 of its sides, it's going to have hydrogens. Now, what are these hydrogens? You could have stacked up top. It doesn't matter. All right. So step 2 is to determine the total number of valence electrons. Looking off the periodic table, we see that phosphorus has 5 valence electrons and hydrogen has 1. So 1 plus there's 3 hydrogens. So this gives us 8 valence electrons. All right, from here, we determine the number of bonding pairs by dividing that 8 by 2. And so that gives us 4 bonding pairs. Then we place those bonding pairs and make single bonds between the central atom and the outer ones. So we place 3 of those bonding pairs. So we have 1 pair left. All right, from there, we will add that lone pair onto our outside ones to make sure they've satisfied the octet. Or in our case, since we have hydrogens as the outer ones, it wants to satisfy the duet. So if we look, say, at this left hydrogen here, right now this hydrogen has 2 electrons with it because it's sharing those 2 electrons with this phosphorus. So this left hydrogen is already satisfied. This bottom hydrogen, same thing. It's got 2 electrons with it, so it's satisfied. This right hydrogen, same thing. It's also satisfied. So then we take that lone pair that we still have to put on our picture, and let's look at the central one now to make sure it's happy or satisfied. So phosphorus has 2, 4, 6 electrons around it right now, and it wants to get the octet, so we're going to take that last lone pair and we're going to place it on top of phosphorus there. So now we have, for our 2 checks, we have drawn in 2, 4, 6, 8 valence electrons, which is how many we should have had, and hydrogens have satisfied their duets, and this phosphorus 2, 4, 6, 8 has satisfied the octet. So we are good there. All right, so this time let's look at an ion. Okay, so step 1, draw the skeletal structure. There's just 2 atoms, so we're going to put them right side by side. All right, step 2, count the total number of valence electrons. Carbon has 4, nitrogen has 5, and in this case we have a charge of -1. That -1 tells us that this compound, well, it's actually an ion now, has an extra valence electron here. So we're going to add on 1 more electron to account for that minus charge. So in total, we have 10 valence electrons. From there, you take your valence electrons, divide it by 2 to get bonding pairs. So we have 5 bonding pairs. All right, then we place a single bond between central and outer atoms. There's just 2 here, so we just draw 1 single bond. We used up 1 of our bonding pairs, so we have 4 pairs left. All right, next is to satisfy the octet around your outside atoms. So they're both outside atoms in this case, So if we start with this left carbon, right now this left carbon has 2 electrons assigned with it. It's sharing those 2 with this nitrogen, but it wants 8. So let's take 3 of those pairs that we have left to draw and give them to carbon. So now carbon has 2, 4, 6, 8. So we have one more pair that we can add. So let's give it to nitrogen. Well, now nitrogen only has 2, 4. So although carbon is satisfied, nitrogen is not. So what we can do when we have atoms, adjacent atoms, so side by side, where one is satisfied and the other one is not, we can move one of these lone pairs and make a multiple bond. So in this case, we're going to take away carbon's lone pair, and instead of that lone pair being just with carbon, how about we share those electrons between both carbon and nitrogen? So we have, in this case, carbon double bonded nitrogen, and then nitrogen has a lone pair and carbon has 2 lone pairs. So now let's check and see if that works. Carbon has 2, 4, 6, 8, so carbon's still good. Now nitrogen has 2, 4, 6, so nitrogen is still not satisfying the octet rule. So let's do the same thing again. Let's take one of these lone pairs that carbon has just to itself and make carbon share that with nitrogen. So this is going to give us carbon triple bonded to nitrogen, and each of them has their own, like one set of lone pair, like one lone pair. So now carbon has 2, 4, 6, 8, and nitrogen has 2, 4, 6, 8. So both of them are satisfied. All right, and then this lone pair that I left on the side of carbon, it doesn't matter if you leave it on top of carbon or in the bottom, and same with nitrogen's lone pair. You can leave it up top, to the side, or on the bottom. All right, and then one thing we got to remember to do, this is an ion, and remember earlier I said once you've drawn the Lewis structure for an ion, you need to bracket that structure and put the charge of it on the outside of the bracket. All right, so there's our Lewis structure for this one. All right, let's look at carbon dioxide. So CO2. We got 3 atoms, so we have to determine who's the central one. We have carbon or oxygen. Carbon is less electronegative than oxygen, and if you remember on that slide too, I said that often carbon is a central atom. All right, so once you've drawn your Lewis structure, or your skeletal structure, and count valence electrons, so carbon has 4, each oxygen has 6, and there's 2 oxygens. So 4 plus 6 plus 6 gives us 16 valence electrons. Then determine your bonding pairs. So we have 16 divided by 2 gives us 8 bonding pairs. All right, and then place single bonds between the central and outside atoms. So we used up 2 of those bonding pairs, and now we have 6 pairs left. All right, from there, we need to place lone pairs on the outer atoms to satisfy their octets, or duet for hydrogen, but we don't have hydrogen in this case. So if we start with this left oxygen, currently this left oxygen has 2 electrons being shared with it. So it wants 6 more. So let's place 3 of those lone pairs around the left oxygen, and now this oxygen has 2, 4, 6, 8. So now this left oxygen's good, and let's jump over to the right one. Same kind of thing. It has 2 with it, it wants 6 more, so let's give it 3 pairs as well. So now this right oxygen has 2, 4, 6, 8 electrons with it, and we have added in all of our lone pairs we had left to give. So now we got to check the central one. Carbon has 2, 4. It wants 8. But if we look at both of its neighbors, so this left oxygen and the right oxygen both have lone pairs and they're both satisfied. So how about we make them give up a lone pair and make a double bond. So if we have this left oxygen donate one of its lone pairs to make a double bond, now we have for the central carbon 2, 4, 6. So it's still not satisfied. So how about we do the same thing to the right oxygen? And there's a reason that we're taking one from each, and we're not going to take both of the lone pair or two lone pairs from the left oxygen and make a triple bond on one side. And we'll look at that here in just a moment. That's going to be on something called formal charges. So we take that lone pair and we're going to move it to make a double bond. So now we have oxygen double bonded to carbon, double bonded to oxygen, and both of those oxygens have two lone pairs left. So now, if we were to check our Lewis structure, we've drawn in 2, 4, 6, 8, 10, 12, 14, 16 valence electrons, which is how many we should have drawn in. And then to check to make sure we've satisfied all the octets, we got 2, 4, 6, 8 for this left oxygen, 2, 4, 6, 8 for carbon, 2, 4, 6, 8 for this right oxygen. So we have satisfied all the octets. All right, before we jump into formal charges, let's look at one more example here, because in some cases you can have more than one central atom. So for instance, in this example here, we have C2H4. Again, carbons are often central atoms. We have two carbons, so both of them in this case can serve as a central atom. So we have carbon and carbon, and around those carbons we're going to have hydrogens as the outside. Now, in a lot of these, especially if you see like a hydrocarbon like this, those are often like, they have some kind of symmetry, is what I'm getting at. So that means two of these hydrogens are going to be assigned to each of those carbons. Now here I drew the hydrogens up top and bottom. You could have drawn one to the side and then one up top or bottom. All right, so after the skeletal structure, count your valence electrons. So carbon has 4 and there's 2 carbons, so 4 plus 4. Hydrogen has 1 and there's 4 of those. So in total this gives us 12 valence electrons. All right, after that you need to determine your bonding pairs. So divide that by 2, and that gives us 6 bonding pairs. All right, then place single bonds from the central to outer atoms. And then you're going to subtract off how many bonds you place. So we placed 1, 2, 3, 4, 5 pairs. So we only have 1 bonding pair left. Or 1 pair left. All right, so typically we take that leftover pair and place it on an outer one, and then to satisfy their octets. But in this case we have hydrogen, so it just wants to do it. If we look at this top left hydrogen, right now it has 2 electrons being shared with it, so it is satisfied. Same thing with this bottom left hydrogen and the top right hydrogen and the bottom right hydrogen. So all of the hydrogens are satisfied. Next, if we jump to the central atoms and check whether they are satisfying the octet. So let's look at this left carbon first. Right now it has 2, 4, 6 electrons with it. So it is not satisfied. Same kind of deal with the right hydrogen, 2, 4, 6. So neither one of these, or did I say hydrogen? Sorry, carbon. The right carbon has 2, 4, 6 electrons with it. So neither one of these carbons are satisfied. We have 1 pair left. We could give it to one of the carbons, so then one of them would be satisfied, but then the other one would not be. So since they both need 2 more electrons, and we have precisely 2 more to give, and they're adjacent to one another, let's just take that lone pair and make a double bond between those two central carbons. All right, so then we can check, have we added in all the valence electrons? We got 2, 4, 6, 8, 10, 12. Yep. Then have we satisfied octets for everything or duets for hydrogen? Hydrogen has 2, 2, 2, 2. And then the carbon, 2, 4, 6, 8. And same thing with this right carbon, 2, 4, 6, 8. So now we are good from there. All right. Now, I mentioned this earlier, this idea of formal charge, because sometimes you'll have to consider who is the most suitable Lewis model, and you'll have to do that with this idea of formal charge, okay? So the formal charge comes into play when you have multiple structures and all of them are satisfying the octet rule. And you're trying to determine, okay, which is the best structure. So instead you use this idea of formal charge. So if we look here at the Lewis structures for SCN minus, we have that this sulfur on the left, say in the leftmost structure, so structure A, the sulfur atom has 2, 4, 6, 8 electrons with it. The carbon has 2, 4, 6, 8. Nitrogen has 2, 4, 6, 8. And you could count the electrons around the S, C, and N in structures B and C, and you will see that they are also satisfying the octet rule. So currently, as is, each of these structures are equally good. But once we add in this concept of formal charge, we will see that they're not actually equally acceptable structures, okay? So formal charge you can think of as the charge the atom would have if all of the atoms in the molecule had the same electronegativity. And if they all had the same electronegativity, what that means is they are going to share their bonding pairs equally, okay? And essentially this is going to just help you identify the best Lewis structure, but it's not a real charge, okay? So formal charges aren't actual real charges. To calculate the formal charge, you would take the valence electrons that the atom typically has, like just going off the periodic table. Then you would subtract off the lone pair electrons around that specific atom, and then you would subtract off the number of bonds, because again, we're going to assume for formal charge calculations that the atoms in the molecule will have the same electronegativity. That means if there's a bond between a carbon and say an oxygen atom, we're going to treat it as if those two electrons between that carbon and oxygen are shared equally. So carbon would get one of those electrons and oxygen would get the other electron for the calculations of formal charge. So let's do an example. Let's go back to earlier, we looked at CN minus. And we had a lone pair on both the carbon and the nitrogen atoms. So let's look at this carbon one here. Carbon typically has 4 valence electrons. Well, I mean, it does have 4 if you look on the periodic table. So carbon has 4 valence electrons minus, we're going to consider all of the electrons that are assigned specifically to carbon. So carbon has 2 electrons in a lone pair. So those 2 electrons are specific to carbon. So 4 minus 2 minus. Again, we're treating, let's suppose that carbon and nitrogen have the same electronegativity. And then we're going to say, okay, they are sharing all of these electrons in these bonds equally. So this carbon would get 1, 2, 3 electrons from these bonds. So carbon would have 4 minus 2 minus 3, which is going to give a formal charge of -1. What formal charge kind of does is, again, it looks at how many valence electrons the atom has, and then how many electrons are actually kind of assigned to it. So we have 1, 2, 3, 4, 5. It has 1 extra electron assigned to it than the number of valence electrons it would have. So since it has one extra negative thing, it has a -1 formal charge. Now, if we look at nitrogen and do the same kind of thing, nitrogen typically, or it has 5 valence electrons. Minus, there's 2 electrons specific to it in these in this lone pair. Minus, there's 3 bonds between carbon and nitrogen, so it would get half those electrons, or 3. So nitrogen has a formal charge here of 5 minus 2 minus 3, which is 0. Okay. Now, when you are using formal charges to pick the most suitable Lewis structure, the guidelines are that you would generally want to pick the one that has the values closest to 0. Okay, so that's the first kind of step or guideline. And then if that's not possible, if you, regardless of how you're drawing your Lewis structures, if the only way you can satisfy the octet is to have a formal charge or formal charges on one or more of the atoms, then what you're going to want to do is make or pick the structure that would give the more or the negative charge to the more electronegative atom. So if we look back up here at that carbon dioxide example, so earlier I said that we took a lone pair from those oxygens that we originally had on them and we made it double bonds on both sides. So the reason that we couldn't have made a triple bond on one side is because we would get a formal charge. So if we look here at this oxygen in the left structure, oxygen has 6 valence electrons. There's 2, 4 lone pairs, so 6 minus 4, and then minus 2 more because of these bonds. That gives a formal charge of 0. If we do a similar thing for carbon, its formal charge is 0. And then for the right oxygen, its formal charge is also 0. However, if we look at the right structure, the structure on the right, we have, for the left oxygen, we would get a formal charge of -1. Because oxygen has 6 valence electrons, but right now in this picture, there's 2, 4, 6, 7 valence, or 7 electrons being assigned to it. So that gives us a formal charge of -1. Carbon would still have a formal charge of 0, and then the right oxygen would get a formal charge of +1 because there's 1, 2, 3, 4, 5 electrons assigned to it. So we would go with the left structure instead of the right structure, even though both satisfy the octet rule, because the left structure is giving us formal charges of 0, whereas the right one does not. All right, so taking that idea of formal charge back to that original, or that question we had earlier. So if we look at those 3 Lewis structures to determine who's the best one, again, we're going to want to assign formal charges. So sulfur has 6 valence electrons. And here in this picture, there's 2, 4, 6, 7 electrons assigned to it. So that gives a -1 formal charge for sulfur. Carbon has 4 valence electrons, and there's 1, 2, 3, 4 electrons assigned to it, so its formal charge is 0 in this case. And then nitrogen has 5 valence electrons, and right now there's 1, 2, 3, 4, 5 electrons assigned to it, so it's also 0. In picture B, sulfur has 1, 2, 3, 4, 5, 6 valence 6 electrons assigned to it, and it has 6 valence electrons, so its formal charge is 0. Carbon, in this case, is going to be 0 again, because we have 1, 2, 3, 4 electrons assigned to it, and its valence electrons are 4. This right nitrogen here would have 1, 2, 3, 4, 5, 6 electrons assigned to it. So it typically has 5 valence electrons. Minus 6 gives it a formal charge of -1. The picture C, so the sulfur has 1, 2, 3, 4, 5, and it has 6 valence electrons, so it has a formal charge of +1. This carbon, again, is going to be 0, and this nitrogen is going to be 1, 2, 3, 4, 5, 6, 7. So it gets a formal charge of -2. All right, so trying to determine who is the best structure, B is going to be our preferable one. So we're going to toss out C because we have two atoms here that both have formal charges, and generally we want our formal charges to be 0 or as low as they could be. And in this case, so now we're looking at A versus B. In A, the -1 formal charge is assigned to the sulfur, whereas in B, the -1 formal charge is assigned to nitrogen. If we're trying to determine which structure is the better one, we want the negative formal charge to be on the more electronegative atom. Nitrogen is more electronegative than sulfur, so we would rather that nitrogen have the -1 formal charge. It would make more sense for nitrogen to have more electrons around it than the valence electrons it would generally have. Okay, so in this case, that's going to be B. Okay. Again, nitrogen's more electronegative, so it would make sense that it would have more electrons around it in the Lewis structure than valence electrons that it has. All right. Another idea we have with Lewis structures is resonance structures. So in resonance structures, first, you identify resonance with this like a single double-headed arrow. So it's not the same as our equilibrium arrows. That's actually two separate arrows stacked on top of one another, and it's half arrows. But for resonance, it's going to be double-sided arrows and one arrow. Okay, so resonance structures are ones in which the positions of the atoms themselves are not changing. What is changing between them is just the position of the electrons. So if we look at this resonance structure for O3, or these resonance structures for O3, sorry, in the left picture, we have oxygen single bonded to oxygen and then double bonded to the other oxygen. Whereas in the right one, it's double bond and then single bond. So all we've done from the left to the right picture is switch the placement of that double bond, okay? So instead of being, and one of those lone pairs, of course. So instead of being single bond and then double bond, it's now going to be double bond and then single bond. But these atoms themselves aren't switching. So it's not that we flipped the molecule, all we did is move the electrons. Now, an important note about resonance structures is that they're an average of these structures. It's not that O3 is oscillating between the left structure and the right one, as in it doesn't. Sometimes it's the left structure, and then all of a sudden it's going to switch and then become the right structure. It's an average. So like some of the molecules could look like the left one and some would look like the right one. Okay. You also will see resonance in other more complicated structures such as benzene, and let's see. Let's do an example. All right, so say we are looking at NO2 minus, the ion known as nitrite. So if we are drawing the Lewis structure for NO2 minus, first we're going to have the skeletal structure. Then we count valence electrons. So nitrogen has 5, oxygen has 6. And then don't forget to add on an electron because of that negative charge there. So in total we have, let's see, 18 valence electrons. Divide that by 2 and that gives 9 bonding pairs. Place single bonds from the central to outer atoms, and then we've added in 2, so that gives us 8 pairs left. So then place lone pairs on the outer ones to satisfy their octet. So now oxygen has 2, 4, 6, 8, and then do the same thing for the right oxygen. And then, so we placed 1, 2, 3, 4, 5, 6 pairs. So we still have, oops, sorry, I messed up in my math a little bit just a minute ago. 9 minus 2 is 7, not 8. So we placed 1, 2, 3, 4, 5, 6 of our 7 pairs. So we only have 1 pair left. If we go back now and check the central atom to make sure it satisfied the octet, right now nitrogen has 2, 4 electrons being shared with it in total. And it wants 8. So we can give our last lone pair to nitrogen, but it's still not satisfied. So it's adjacent or beside 2 oxygen atoms that are satisfied and have lone pairs. So what we can do is take one of the lone pairs from one of these oxygen atoms and make it a double bond, so that way it's sharing those electrons with nitrogen. So let's say we take it from the left oxygen. So that would give us oxygen with 2 lone pairs double bonded to nitrogen has 1 lone pair that is single bonded to another oxygen with 3 lone pairs. Now, here in this example, I took it from the left oxygen. And sorry, before we forget, let's put brackets and then the charge, because this is an ion. All right, so again, I took it from a lone pair from the left oxygen to make a double bond. But the right oxygen was just like the left one, so why couldn't I have taken it from the right one? Well, resonance structures tell us that we could. So let's draw that structure. So now this time we're going to change the position of the electrons, so that way it's oxygen with 3 lone pairs single bonded to nitrogen, and then double bonded to the other oxygen. Okay, so all we've done here is change the positions of the electrons. We haven't changed the position of the atoms themselves, and let's put our negative up there. So this would be an example of something that has a resonance structure. Now, sometimes on AP FRQs I've seen, they have specifically stated or mentioned draw these structures or make sure you include resonance structures. But if it has resonance structures, then you need to make sure you do draw in the resonance structures, because it's not that all of the molecules of, or all of the ions, NO2 minus, don't necessarily look like this left structure, or they don't necessarily look like the right one. In general, we just say it's an average between these two structures. So you would need to draw both of them. All right. So last, real quick, I'm going to mention, and it talks about this too in our review books, but there are, of course, just like a lot of things in science or chemistry, there's exceptions to these Lewis structures and to the octet rules. So our 3 primary exceptions could be that we have molecules or ions that are going to give us an odd number of electrons. So we wouldn't have an exact even number of bonding pairs. You would have so many bonding pairs and then 1 extra electron that you would have to still add in, okay? And then you could also have molecules or ions that have an atom with less than an octet, or you could have some instances where one of the atoms has more electrons around it, so that way it is overshooting the octet, so it has more than what the octet says it should have. All right, so again here, one of the exceptions could be an odd number of electrons. So for instance, if we looked at NO2, it would give us 17 valence electrons. So what that means is that 1 extra electron is just, we have to add it in, because you absolutely have to draw in all of the valence electrons you are starting with, but that 1 extra electron is just going to be on one of the atoms. So In this case, once you draw the Lewis structure, it would be assigned to oxygen. And then you could have instances where an atom has less than the octet. A lot of compounds too that would have less than the octet rule would be boron or beryllium compounds. So other examples too, let me jump through here, where we'd have more than the octet could be, or generally you're going to see them for elements that's in period 3 and beyond. All right, so like I said, it mentions it in the review book, and often our Lewis structures that we're drawing are going to satisfy the octet and won't include these exceptions. But just in case you do come across one of these compounds, know that there are some instances where you have exceptions to the octet rule. All right, so that is all for this video, and then in the next one I will cover bond enthalpies and VSEPR theory.